The white grains pass through the lips and fall onto the tongue. Saliva immediately envelops them, forming a transparent film that penetrates every surface of the compacted starch. The body temperature of 37 degrees begins to disintegrate the outer layers, while salivary amylase, released from the parotid glands, begins its silent work. The molecular chains of carbohydrates start to fragment in the moist darkness of the oral cavity. Teeth press repeatedly against the grains, crushing their crystalline structure until they become a semi-liquid paste mixed with digestive enzymes. The texture changes constantly, from solid to viscous, as the tongue pushes the mass towards the back of the throat. The food bolus descends through the esophagus in peristaltic waves that compress the muscular walls. The pressure is constant, rhythmic, pushing the whitish mass downward in the total darkness of the digestive tube. The walls contract and expand, generating a serpentine movement that drags the rice fragments wrapped in thick saliva. Temperature remains stable, but humidity increases as mucus glands secrete more lubricating fluid. The journey lasts only seconds, but each centimeter traveled intensifies the initial molecular breakdown. The mass reaches the lower esophageal sphincter and passes through the muscular ring that separates the esophagus from the stomach. The gastric cavity receives the rice with a release of hydrochloric acid. The pH drops drastically to levels close to 2, creating a corrosive environment that rapidly dissolves the remaining structure of the grains. The stomach walls, coated with protective mucus, contract vigorously in peristaltic movements that mix the contents like a biological blender. The rice becomes an acidic slurry called chyme, losing all recognizable form. Pepsin, a proteolytic enzyme, begins to attack the scarce proteins present, while starch continues fragmenting into simpler molecules. The stomach fills with gases produced by initial fermentation, creating pressure against the distended walls. Internal temperature increases slightly due to intense chemical activity. The chyme remains between 2 and 4 hours in this primary digestion chamber, constantly agitated in the acidic bath. The pylorus opens intermittently, releasing small amounts of chyme into the duodenum. The contrast is immediate. The extremely acidic environment meets the alkalinity of the small intestine. The pancreas releases sodium bicarbonate that neutralizes the acid, while simultaneously releasing pancreatic amylase in abundant concentrations. This enzyme effectively attacks the remaining starch chains, splitting them into maltose and dextrins. The gallbladder contracts, expelling yellow-green bile that emulsifies the minimal fats present in the rice. The bile fluid mixes with the chyme, creating a creamy suspension that flows slowly through the intestinal villi. The walls of the duodenum absorb water and electrolytes, gradually concentrating the contents. In the jejunum, absorption intensifies dramatically. The intestinal villi, microscopic projections that increase the surface area of contact, are covered with specialized epithelial cells. Each cell has microvilli that form the brush border, a structure designed to capture glucose molecules. Maltase and other disaccharidases, anchored in these cell membranes, complete the final digestion of starch. Maltose molecules are split into 2 units of glucose. Each glucose molecule crosses cell membranes through specific transporters called SGLT1 and GLUT2. The process is massive and simultaneous. Millions of glucose molecules enter the bloodstream within minutes. Blood sugar concentration begins to rise rapidly, triggering a hormonal cascade. The pancreas detects the increase in circulating glucose through specialized beta cells in the islets of Langerhans. The response is immediate. Beta cells release insulin in amounts proportional to the glycemic spike. The hormone travels through the bloodstream, reaching every tissue in the organism. Muscle and adipose cells activate their insulin receptors, opening channels that allow glucose to enter. In muscles, part of the glucose is converted into glycogen for temporary storage. But when muscle stores become saturated, insulin redirects the excess toward adipocytes. Fat cells absorb the surplus glucose and activate lipogenic enzymes that convert carbohydrates into triglycerides. Lipid droplets increase in size within adipocytes, expanding fat tissue imperceptibly but constantly. The liver receives a considerable portion of the absorbed glucose through the hepatic portal vein. Hepatocytes, highly metabolizing liver cells, capture sugar molecules via GLUT2 transporters. Part of the glucose is stored as hepatic glycogen, filling cellular stores to their maximum capacity. Excess activates the glycolytic pathway, breaking glucose down into pyruvate. When energy demand is low, pyruvate is diverted toward de novo lipogenesis, a process that synthesizes fatty acids from carbohydrates. Newly formed triglycerides are packaged into very low-density lipoproteins, VLDL, which are released into the bloodstream. These particles circulate, depositing fat in peripheral tissues and gradually contributing to visceral lipid accumulation. The brain registers the glucose spike with remarkable precision. Glucose crosses the blood, brain barrier through GLUT1 and GLUT3 transporters, directly fueling energy-hungry neurons. The hypothalamus detects energy abundance and modulates neurotransmitter release. Dopamine is released in moderate amounts in the nucleus accumbens, generating a subtle sensation of satisfaction. However, the response is less intense than with simple sugars, creating a moderate neural reward that does not trigger significant euphoria. Temporary satiety is established when leptin, secreted by filled adipocytes, signals to the hypothalamus that energy stores are increasing. But the satiety window is brief, since circulating insulin promotes active glucose uptake, causing a secondary drop in blood levels. Approximately 90 minutes after ingestion, blood glucose begins to decline. Persistent insulin continues directing glucose into cells even after the spike has passed. Blood levels fall below the basal point, creating mild reactive hypoglycemia. The brain interprets this drop as a signal of energy scarcity. The hypothalamus activates the release of ghrelin from the stomach, a hormone that stimulates appetite. Simultaneously, the adrenal glands secrete cortisol in response to perceived metabolic stress. Cortisol mobilizes glucose reserves through hepatic gluconeogenesis, but it also promotes abdominal fat retention. The hunger-satiety-hunger cycle restarts, driving the search for more food. In the large intestine, the minimal residual fibers of white rice offer little substrate for the intestinal microbiota. Colonic bacteria, deprived of fermentable fiber, reduce their production of short-chain fatty acids such as butyrate. Without enough butyrate, colon cells lose their preferred energy source, affecting the integrity of the intestinal barrier. Permeability increases subtly, allowing bacterial endotoxins such as lipopolysaccharides to pass into the bloodstream. The immune system detects these foreign molecules and activates a low-grade inflammatory response. Macrophages release pro-inflammatory cytokines. Interleukin-6, tumor necrosis factor alpha, C-reactive protein. These molecules circulate systemically, creating an imperceptible state of chronic inflammation that affects multiple tissues. Endothelial cells lining blood vessels respond to persistent inflammation and repeated spikes of glucose and insulin. Transient hyperglycemia generates free radicals through non-enzymatic glycation of proteins. These advanced glycation end products, AGEs, accumulate in arterial walls, gradually stiffening them. Chronically elevated insulin stimulates the proliferation of vascular smooth muscle cells, thickening the arterial intima. Circulating monocytes adhere to the inflamed endothelium, penetrate the vascular wall, and transform into lipid-laden macrophages, forming foam cells. These cells initiate the formation of atherosclerotic plaques that develop silently for years. Visceral adipose tissue, located deep around the abdominal organs, responds particularly actively to repeated glycemic load. Visceral adipocytes, more metabolically active than subcutaneous ones, continuously capture triglycerides. As they expand, they release pro-inflammatory adipokines such as resistin and visvetin. Leptin, although present in high concentrations, loses effectiveness due to resistance developed in hypothalamic receptors. Adiponectin, a protective hormone, decreases in inverse proportion to the increase in visceral fat. The hormonal imbalance perpetuates insulin resistance, creating a vicious circle in which each meal rich in refined starch worsens metabolic sensitivity. The endocrine pancreas works constantly under increasing pressure. Beta cells hypertrophy, increasing their size to produce more insulin in response to peripheral resistance. Excessive and sustained demand generates stress in the cellular endoplasmic reticulum, where insulin proteins are folded and processed. Oxidative stress within beta cells increases, producing reactive oxygen species that damage mitochondrial DNA. Some beta cells enter apoptosis, programmed cell death, gradually reducing the pancreas's secretory capacity. The process is slow but continuous, establishing the molecular basis for eventual pancreatic insufficiency. In hepatocytes, de novo lipogenesis continues after each rice load. Synthesized triglycerides accumulate when they exceed export capacity via VLDL. Intracellular lipid droplets increase in size and number, creating non-alcoholic fatty liver. Hepatic steatosis interferes with the organ's normal metabolic function. Insulin sensitivity decreases in liver tissue, perpetuating basal hyperglycemia. Inflamed liver cells release transaminase enzymes in elevated amounts, silent markers of organ damage that can remain undetected for years. Low-grade systemic inflammation also affects the brain in the long term. Pro-inflammatory cytokines cross the blood, brain barrier, and interact with microglia, the immune cells of the central nervous system. Activated microglia release more inflammatory mediators, creating localized neuroinflammation. neurogenesis in the hippocampus, the process of forming new neurons, is compromised. Synaptic plasticity decreases, affecting memory and learning in a subtle but measurable way. Insulin receptors in neurons lose sensitivity, a phenomenon associated with progressive cognitive dysfunction and neurodegenerative risk. The kidneys continuously filter blood loaded with glucose, insulin, and metabolic products. Sustained hyperglycemia causes glomerular hyperfiltration, forcing nephrons to work above their normal capacity. Podocytes, specialized cells that form the filtration barrier, suffer mechanical and oxidative damage. The glomerular basement membrane gradually thickens, reducing filtration efficiency. Proteins begin to be filtered in abnormal amounts, an early sign of nephropathy that usually goes unnoticed until advanced stages. The cardiovascular system responds to the metabolic load with adaptations that initially appear protective, but eventually become problematic. The heart, constantly exposed to elevated insulin levels, develops left ventricular hypertrophy. The heart muscle thickens to maintain cardiac output against increased vascular resistance. However, thickening reduces ventricular flexibility and compromises diastolic filling. Blood pressure tends to rise due to insulin-mediated sodium retention and vasoconstriction induced by activation of the renin-angiotensin-aldosterone system. Circulating immune cells, exposed to repeated patterns of glycemic fluctuation and chronic inflammation, alter their activation pattern. Neutrophils show increased production of reactive oxygen species, increasing systemic oxidative stress. Regulatory T lymphocytes, responsible for modulating the immune response and preventing autoimmunity, decrease in number and functionality. Immune balance shifts toward a pro-inflammatory state that increases susceptibility to infections and autoimmune diseases. Skeletal muscle mass, although it initially responds well to insulin, begins to show resistance after chronic exposure. Insulin receptors in muscle membranes are internalized less efficiently. Intracellular signaling pathways become desensitized due to constant activation. Muscle takes up less glucose and synthesizes less glycogen, redirecting even more carbohydrates toward adipose tissue. Body composition gradually changes, with a relative loss of lean mass and an accumulation of fat, even without obvious changes in total weight. The white grains, seemingly innocent, trigger a metabolic cascade that reverberates for hours after ingestion. Each organ responds, adapts, subtly inflames. The body works tirelessly to process, store, neutralize. But daily repetition of this process, meal after meal, year after year, transforms temporary adaptations into permanent changes. The rice disappears from the digestive tract, but its molecular impact persists in every cell, in every tissue, silently shaping the metabolic destiny of the organism. If you want to continue understanding what happens inside your body with each habit, subscribe to the channel and activate the bell, so you don't miss this journey of what happens inside your body. We'll see you at the next habit.